Today, I want to explore something I've been thinking about a lot, and that is using two microphones for time-dependent measurements in-car audio rather than relying on one, and what benefits it can bring. Because at this point, it's changed the way I tune, and I have way better results, and I'm excited to share that, hoping that someone else can pick up the method and see the improvements I experience in their own vehicle. So that's the goal of why I'm talking about this. Okay, so to lay a quick foundation for the discussion. So this is an overhead view of the vehicle. We have mid-range in the dash, our tweeters in the sail panels, mid-bass in the door, sub in the trunk, and pretty standard three-way configuration. We have our driver in the listening position, and he is oriented his head towards center stage. My last video wanted to determine where the ideal measurement microphone location was, because I wasn't happy with the solutions I saw online on where to place the microphone. They seemed very generic and with no real quantifiable evidence behind why you should place them there, except I thought it sounded the best and it worked for me. And there's validity to that, but I wanted something measurable, and I wanted to know that that was actually the place I had the least error for, because I wasn't getting consistent measurements. It would change every time I tried to set it up in my vehicle to some degree. I found the location of least error in my car, but I wasn't happy with the amount of uncertainty there was in the location. It was too high for my goals. And it only got worse from there because, one, it was theoretical error. So in reality, in the real world, you're gonna get a lot higher error with that. We're not perfect, and we can't place the microphone in the exact right location every time. I mean, that's one of the initial problems I was having. Two, it only considered 2D space. So the second you look in 3D space, the error gets much larger, and so it wasn't addressing the full geometry of audio. And then three, it wasn't very generalizable, especially when you consider all of the possible different ways people can install speakers in their vehicles. And the more speakers you add, the worse that uncertainty gets. And that's when I realized a solution that encompassed the entire problem. And it's not a new idea, but it's using two microphones for each ear rather than simplifying the ears down into one location. Two microphones resolves the issue of the error between the ear and where the microphone's placed. So the initial assumptions are left speakers aligned to left ear, right speakers aligned to right ear. So any error that was in the measurement was the difference in timing that that ear experienced relative to the microphone. So because they're physically different in space, that sound is going to hit your ear before it would hit the microphone. And then you can quantify that error, and you can add them up for all the speakers to map the space in terms of, okay, what is the error at each location? And then you can use that map of the space to figure out where the point of lowest error is. So that's what I did. If you took two microphones and you place them at each of the ear, then that completely solves the original problem. Because now you have no location uncertainty, and it also addresses the problem in 3D space. Because again, there's no location uncertainty. You put them right in the ear, and then you have all of the data that's coming into each ear for any possible speaker. It captures all of the way we localize sound, because we're not simplifying our ears down into a single point in space. And it's also very generalizable, because I don't have to do a calculation every time I want to figure out where the best place to put the mic is in my car, and then try to figure out where that location is in the real world. Like, there's that problem is addressed. And So now you're only dependent on the small uncertainty between your head movements, or that maybe where your eardrums are versus your ears, right? The uncertainty is very, very small, so you've addressed that part of the problem. Okay, so let's assume, like I am, that this is the correct approach to tune. It gives you a more complete picture of how to do timing measurements in your car. Well, the next question is pretty fun. It's now, how do I use 2 points of data to tune and set up my system properly? Because it's a different game than relying on 1 point. And then what considerations do I take when I'm setting up that those 2 microphones in space? Okay, so to address how to set it up, this is my approach. So you go into your car and you sit and you figure out where your ears are in the car, but you have to have your head oriented towards your center. That's an important part of this discussion that I haven't really seen addressed, if ever. And why am I under the belief that that's a very important part of this discussion? Okay, so let's think about how our brain localizes sound. When I'm standing directly in front of you and you're talking to me, I know that you are directly in front of me because I hear the sound from in my left and my right ear at the same time. I mean, there's other factors that go into that, obviously, but we're only looking at the timing world, so that's how my brain localizes cues, is that direct sound arrives in both ears at the same time. Now, when I turn my head, I'm hearing that sound in one ear earlier than I'm hearing it in the other ear, and that small timing difference helps me figure out where in space you're oriented. If we have the hearing threshold to be able to turn my head a few degrees over and I can hear that change in space, why shouldn't we be that sensitive with our measurements? We need to consider that, if that's part of the way our brain localizes sound. If we do our timing measurements with the 2 microphones where our ears are when we're looking at center, then our center stage will fall into place perfectly because it's recreating that illusion that when it's arriving at the same time, it's directly in front of me. The cool thing about that is after you've lined up center and you've recreated the center illusion, that imaging illusion, well then anytime you turn your head, your brain is already calibrating where that sound's coming from relative to the center, and everything magically falls into place. It's really astonishing how just it changed the way I experienced tuning. I'm excited to share it. So that's how you set it up. You sit in your car, you look towards center, you find where your ears are, and that's where you place the microphone. Okay, so the next question to address is, how do we tune the system? And before we get into the discussion, I just want to highlight something that I think is important to call out now and have you think about as we talk about this, is that time domain and the frequency domain represent the same thing. In the time domain, we're looking at our pressure waveform over time, and with an impulse response, we are sending a spike through the system and then nothing, and then seeing how that data comes into our microphone. And so we know we sent the spike out 30 milliseconds ago and it just hits our mic then, and we can get an idea of how far the speakers are away. Okay, now our frequency domain, when we look at the phase graphs, it's telling you the same thing. It's the same unit, but flipped on itself. It's inverse seconds. And what the phase chart tells you is when each frequency arrived at the microphone. So before, we're looking at a high level view of, okay, I can see when the initial impulse came into the system and what it looks like after it's been modulated by the filters and by the environment. And I can use that to get an idea of the relative delays. But you can see the same thing in the frequency domain by looking at when each frequency arrived. That's all the phase is, and it's not some magical thing that wraps. If you actually look at the phase, it's one big continuous chart, and we just, only look at it through, 2 pi or 360 degrees because we can't have some continuous graph going on forever. So when we do phase alignment, we're aligning each frequency. And that's really useful for that purpose. But when we're doing time alignment for higher frequencies based on impulse response, a lot of those phases get so messy and so wonky, especially if you have an infinite impulse response system, a DSP that induces phase distortions. And then you have all the reflections. It can be really hard to measure the high frequencies with phase. So we use impulse response. And the cool thing is, our brain does the same thing. When we hear high frequencies, we look for timing cues. So when that direct sound hit one ear or the next. Because the amplitude is already cycled a ton of times before it hits the other ear. So we can't use the phase to discern the timing. When we have really low frequencies with really long wavelengths, well then we use the amplitude difference and the pressure between our ears to tell where that sound's coming from. Because they're so long that we can discern high pressure in this ear, lower pressure in this ear. I have an idea of where that sound's coming from. And that's why with subwoofers, you really can't localize them. It's because the wavelengths are so long. And so our ears can't tell the difference between the pressure in this ear and the pressure in this ear. And so we can't figure out where it's coming from. Okay, so that sort of sets up the kind of psychoacoustic parameters for how we're gonna address this system. We're gonna start in the time domain for our highs, and then we're gonna move down to the frequency domain for our low frequencies. And that one is consistent with, or more convenient for tuning with SMART, and it's also consistent with our psychoacoustic models, but you can go back and forth as you need, because again, they represent the same thing. Okay. So we start with our highs, and you look at the impulse from the left speaker to the left mic, and you align that right over the time difference from the right speaker to the right mic, assuming the timing between the two microphones is consistent. That's something you got to consider, but let's say that their zero reference is the same. So you get those two microphones to overlap perfectly. And now your highs are in time. That pair is done. Another thing that's important to consider here is that you want that initial spike in the impulse response to go the same direction for both speakers, because that tells them that they're in phase. If one speaker is pushing, increasing pressure to make that spike go up, and the other speaker is like sucking, I guess, going backwards to make that spike go down, well then those speakers aren't going to play together to construct the sound, they're going to play against each other and destruct the sound. So we want those impulses to go up together, and that's true for all the speakers. Okay, that's how you can tell if your system's in phase or not when looking at the impulse response. Okay, so we have our highs in phase. Now we're going to do the same thing with our mids. We're going to use the impulse response to get those all over each other, but you'll notice when you're tuning, hey, this impulse response is not as clean and perfect as my mid-range response. In fact, the peaks are a lot bigger and they arrive later. There's more of an slower onset than the highs. Okay, well that makes sense, because remember, our highs are super high frequency, and so that initial amplitude, rate of change is really steep. So you'll get to that peak rather quickly. But with your mid-range, it's been filtered for all the highs. And so it's playing a lower frequency, and so that amplitude takes longer to peak. And so in your impulse response graphs, they're gonna look different. They're not gonna be the same nice, clean impulse. And that's good, that's not a bad thing. That means that's expected. But then if you can't overlap them as cleanly as the highs, then what do? Well, you look for the onset. You look for the start of that waveform. And that's how you tell when they're aligned. And that goes back to our hearing, because we localize sound by the direct sound. We use reflections. We can figure out where the reflections came from, but most of the cues rely on direct sound. So you want to look for that first spike to do your timing. Okay, so the mid-range is around where our hearing starts to shift from time domain to frequency domain, the phase. So we want to, when we're aligning our mids and our lows, we want to focus more on the phase charts. So what I do is I use the impulse response to try to get all the subs and the lows sort of roughly at the same time, so I'm not starting out of like nowhere when I'm looking at phase, because you can get pretty close with just the impulse. But then I go ahead and perfect everything in phase. So if everything's worked out well, when you look over to phase, your mid, left, and right phase should be consistent. Now, if they're not, maybe go reevaluate the time domain impulse and see if they're overlapped. But you might need to make some compromises between the lower frequency timing of the mid-range and the higher frequency timing of the mid-range. Because remember, our filters and also our environment distort phase. So you can't expect, especially when you put all these different, parametric filters, or maybe you don't use the same crossovers on each mid-range to get the acoustical slopes to match. You can't expect the timing in that phase to be consistent between all the frequencies. So they're not going to line up perfectly. So you will have to make some sacrifices, but as long as mostly everything's consistent in all the ways you're looking at it, that's where you want to be. So you go into your phase chart, may look like something like this, depending on how you have your timing set up. But you go into each speaker, looking at the correct microphone, and you get all of their phase wraps to line up. So I go to my left and my right mid bass, and I get their phase wraps to line up as much as I can. And I say, okay, this pair is together. And then I time those until that pair is matched to my mid-range pair. And when you do that, if it worked out well and all the phase wraps are lined up, you'll get a nice sum on the magnitude plot in that region. When they're out of phase, and they get sucked out, there's a cancellation. But everything should get like a 6 decibel sum if it's worked out. And then we move on to the subwoofer. But you might say, okay, well, we have 2 ears, but our subwoofer is playing mono. Well, how do I align that? And that's a good question. I have been phase averaging the 2 microphones. So when I look at the sub, I take the left and the right microphone and I average those phase to get roughly the same picture between both. Now, I don't think the sub is as important. I really don't think those few little millimeters will make that much of a difference in the subwoofer, and that's because the wavelengths are so long that our brain can't really discern that well over the highs and the mids. So I don't think it's that critical that we're phase averaging. Now, you could place one in the middle if you don't want to phase average and have 3 mics. I was doing that for a while. Or you could place it in the ideal location like we're talking about, but also that wouldn't really be the ideal for the sub, because the sub is in the back, so you could find the ideal location when just considering one speaker. That's also a possibility, but all the things I've tried, I haven't really noticed a difference. I think that's kind of where it ends for me. But again, I want to also kind of solve this picture completely. So so then you get your phase all together, and with the lows and the timings with the highs, and you make sure everything looks good in both charts, and that's how you tune the system. So I really like this approach. It fits in a lot of my understanding, because I'm a biomedical engineer, so I like the physiology side and the engineering side a lot. So I really love this passion, and I just like how in both models it makes sense with what's convenient for our data, and it also makes sense for how our hearing is designed, and so they fit together well. So that is how I approach the problem. I think next I want to actually take everyone through actually looking at SMART to see what the data really looks like and how to physically interact with the software and your digital signal processor to get the results you want. But I think this provides a lot of important context for what I'll be doing in the future. So yeah, thanks for watching. I'm curious to know what you think. If there are any things that the solution doesn't address, I'd love to hear about it, or just your thoughts overall, because I'm looking to learn, because I don't know everything, obviously. So that's sort of why I'm here. So feel free to engage. I'm open to new ideas on this. So thank you very much.